Python Beats. This video, we are going to look at an introduction to related rates. So what is this? What is these related rates? What are these related rates? That's what I was asking. Well, kind of silly, but rates which are related to one another. So you may have multiple rates within a given equation, and hence they're related in one way or another. And we'd like to introduce this kind of idea in this video before we get into the more robust applications of this. So let's take a look. Let's just start by considering this equation. X squared plus y squared is 16, okay? But we're also going to assume that x is a function of some variable t, and y is also a function of the variable t. So kind of like parametric equations, right? Now, under that assumption, then if I went ahead and differentiated both sides of that equation right here with respect to t, then I'd get this statement right here, right? I'm going to differentiate x squared plus y squared with respect to t, and that better be equal to the derivative of the constant 16 with respect to t. So just applying implicit differentiation, if you will. Now, because both x and y are both functions of t, then I got to apply the chain rule both to x squared and to y squared, right? So x squared, right, is the same as x of t squared, and y squared is the same as y of t squared. So when I differentiate each of those with respect to t, there's a chain rule involved with the general power rule, and hence I get this result, and that is derivative of x with respect to t is going to be the derivative of the inner function, x of t with respect to t. That's my dx dt, or x prime of t, if you will. And the derivative of the outer function, well, bring down that power of 2, and you're left with a power of 1 on the x, so 2x dx dt. And of course, the same thing can be said about the derivative of y squared with respect to t. We see our y prime of t, derivative of the inner function, times 2 times y. And all of that equals 0 because the derivative of a constant with respect to t is 0. So what, right? I mean, this is some of these things we've been looking at. However, keep in mind that equation right above. Let's say we want to find dy dt from here. So we have that equation. That's the relationship thus far. And we want to figure out, what is dy dt? Well then, what can we do? Well, here's our equation again that we were just looking at. I can go ahead and solve that for dy dt, very similar to the process of implicit differentiation. But now I'm going to subtract 2x dx dt on both sides, right? So minus 2x dx dt on both sides of this equation, and that'll help me isolate dy dt, giving me this equation right here. 2y dy dt is equal to negative 2x times dx dt. If I then go ahead and just divide both sides by 2y, then I get dy dt is negative x divided by y times dx dt. And in fact, like I was saying, this is a related rates situation. That's an example of it. Why? Because we have a rate of change on the left-hand side, dy dt. How does y change with respect to t? And it's equal to some other expression, in this case, negative x divided by y times dx dt. But the important thing here is that on the right-hand side, there's another derivative, the dx dt. How does x change with respect to t? And so this equation relates rates. And that's really this topic that we want to start getting into, is situations in which one rate depends on, say, one or more variables, but also depends on at least one or more rate as well. Rates that are related rates. Let's just look at another one, kind of get an idea again. Just make something up. Suppose that we have, again, x and y are both functions of t, and we know that this relationship between x and y is given by sine of x times y is equal to 1 minus x plus y. In this situation, we'd like to figure out what's going on with dx dt. What is it? Now, we use this parameter t as the parameter that tells x and y what to do, but oftentimes we use t to represent time, and eventually we'll look at applications of this. As time changes, what's changing in terms of x, y, or whatever the variables are? But in this situation, we could just keep it arbitrary, just to add a context. So what I have to do here is figure out what dx dt is. In order to do that, I can go ahead and differentiate both sides of the equation with respect to t. So let's do that. All right, so I got dx, or excuse me, d dt, differentiate the left-hand side with respect to t, is sine of xy. I got to differentiate that. And then I'll differentiate with respect to t the right-hand side. So the derivative with respect to t of 1 minus x plus y. Now, again, x and y both functions of t. So anywhere we're differentiating x or y with respect to t, we're going to have to apply the chain rule. On the left-hand side, we have a chain rule, but we also have a product rule because we have sine of x times y. Of course, x times y is really just the same as x of t times y of t, so I have a product of two functions. And so I'll go ahead and write that as d dt of x times y, keeping in mind x and y are both functions of t. That's the derivative of that inner function with respect to t, times the outer function's derivative. The outer function is the sine here, so a cosine of the inner function x times y. On the right, derivative of 1 with respect to t is 0. So we're going to get a minus dx dt because the derivative of x with respect to t is, well, it's the derivative of x with respect to t with that negative sign. Plus, for a similar reason, dy dt, derivative of y with respect to t. Now, on the left-hand side, we still have some differentiating to do. We got that product rule going into effect with the derivative of x times y. The derivative of x with respect to t is dx dt times that y, so I'm going to apply my product rule, y dx dt, plus the x times the derivative of y with respect to t. And all of that is getting multiplied by the cosine of x times y. Now, on the right-hand side, we still have negative dx dt plus the dy dt. Now, the goal here is to isolate the dx dt, so you can see the similarities of implicit differentiation. Now, I'm going to go ahead and distribute the cosine of xy, so I got dx dt terms and dy dt terms on the left-hand side. So when I do that, what am I going to get? I'm going to get, all right, a y times a cosine of xy times dx dt plus an x times the cosine of xy times a dy dt. And all of that is still negative dx dt plus dy dt. So I'm going to bring my dx dt's on one side, my dy dt terms on the other side. I'm going to go ahead and add, right here, add the dx dt to both sides to give on the left-hand side y times cosine of xy dx dt plus a dx dt. And then right here, I'll subtract the x cosine of xy dy dt on both sides to get on the right-hand side dy dt minus x times cosine of xy times dy dt. Now we're almost there. What else can we do? Well, on the left-hand side, let's get that common factor of dx dt. We get dx dt times y cosine of xy plus a 1. And on the right-hand side, we could choose to factor out the dy dt. Why not? Dy dt times the quantity 1 minus x times cosine of xy. It's not going to be a completely necessary, that right-hand side there, but might as well do it because we can. Finally, divide both sides by y cosine of xy plus 1 to get that dx dt is dy dt times 1 minus x times cosine of xy, all divided by y cosine of xy plus a 1. And all of that just to figure out what dx dt is. And on top of that, to show, here's another example in which we have two rates which are related to one another. The dx dt, how does x change with respect to t, is equal to this right-hand side here, and there's another rate of change on that right-hand side, dy dt. So depending on how dy dt changes, and x and y and whatnot, it will tell us how x changes with respect to t. An example of a related rate. And these types of processes are going to be involved when looking at the applications of related rates. And oftentimes, as I mentioned before, we use t for the variable of time. Time is changing, other quantities are changing, and then we start to ask questions. And thus, this kind of situation may arise when we go and we answer those questions. So this video is just to set us up for a little bit of background into getting into the actual applications of related rates. And so we see that this mechanics are involved, and technically when we have a related rate, it's an equation in which we have multiple rates being equated with one another, one way or another. But that's it. That's the video. That's the intro. Next video, applications of related rates. And you know what? Until that time, it's Math and Beats. See ya.